here's a couple of slides addressing some of the frequently asked questions I get on being an astronomer or an astrophysicist. I also, in addition to this video, have a several-page PDF write-up. If that's something you'd be interested in, just let me know. So in terms of classes and education, most astronomers have PhDs, so that means going to college and going to graduate school. It turns out, though, that you will not pay for graduate school. You probably will pay for college, but you will not pay for graduate school. That means you're not going to be racking up debt when you're going to grad school. It's just the way it works in the physical sciences. You end up either working as a teaching assistantship or working as a research assistant tied to somebody's grant. You don't have to pay to go to grad school. It turns out, though, that many people working for NASA or the major telescopes don't have PhDs, but they may be engineers, and that's a separate talk. To be a successful astronomer or astrophysicist, it doesn't matter so much where you go to college. You need to really learn. So you need to go to a place that works for you, whether that's big, small, rural, urban, technical, liberal arts, whatever works for you. It needs to be a supportive environment for you so that you can learn, because you need to cram an awful lot into your head in only 4 years. You need to take as much physics and math and computer science as you can possibly get your hands on. And depending on what kind of an astronomer you want to be, you might also need to load up on the chemistry, the geology, even the biology if you want to look for extraterrestrial life. I recommend that you major in physics because physics is a solid foundation for just about any physical science, especially astrophysics, but it provides a pretty good foundation for chemistry, geology, even biology too. And it turns out that if you decide to do something else after college, I have had really good response to having a degree in physics. Every HR department everywhere, except for possibly here at Caltech, is impressed if you have a degree in physics because they think, oh, you must be really smart. That's a really good impression to leave on people. So that's part of why I recommend majoring in physics. I also recommend that you get your feet into real research as soon as you possibly can. Real research is totally different than classes, and there are plenty of people who do really well in classes that really do not do well in research, and vice versa. People who do really well in research, not so well in classes. So you want to get into real research as soon as you possibly can. Once you get into college, there's lots and lots of opportunities in the summers to do research. Pick up those opportunities as fast as you can, preferably at a different institution from where you're attending classes, so that you get a sense of what other institutions are like and you learn from different people. I myself have my undergraduate degree in physics from the College of William & Mary in Virginia, which is a liberal arts school. Go liberal arts. And I have graduate degrees, my master's and my PhD in astronomy and astrophysics from the University of Chicago. Why do I do astronomy? Well, I've always loved astronomy ever since I was really little. I don't ever remember a time when I was little before I wanted to be an astronomer. I was transfixed by anything having to do with NASA, especially the Voyager images, which came back at just the right time for me to get really, really inspired, especially the images of Jupiter. I admit I totally fell off the wagon for quite a while in elementary school because despite my parents' best efforts, I bought into the idea that girls can't do math, which is totally garbage, obviously, but it took me a long time to get over that and realize that, hey, I can do math, and this is actually pretty cool. I'm doing pretty well. So what do I do now? Well, you may know that professors are hired both to do research and to teach or otherwise serve the university community in some way. I do research, but instead of teaching, I support a spacecraft and archives. I support the Space Telescope, and I support the Infrared Science Archive, or IRSA. It turns out that I have carved out an opportunity to teach on my own. I run a program that helps get teachers into real research called NITARP. I also do science, by which I mean I travel to conferences, I write proposals, I go on observing runs, I prepare space-based observations, I reduce data, I write papers, and I give talks, all of which are part of science. What do I do day to day? Most of the time I'm working on my computers and I'm attending meetings, both online and in person. In astronomy, there are 4 flavors of astronomers. You can be an observer, you can be a theorist, you can be a computer modeler, or you can be an instrument builder. So observers, like me, observe. We collect data, trying to understand what's going on, in my case, in young stars. Theorists take the astrophysical concepts and try to explain how we're getting the data that we're getting, or make predictions for what data we should be getting based on their deep understanding of the physics that goes into modeling these systems. Computer modelers are sort of in between observers and theorists in that they have to be really good at the theory to build really good models, and then they can generate millions of models and study statistically what's more likely or less likely in their model, so they're kind of like observers too. Instrument builders are super important. They're the astronomers that have a foot in the engineering world because they're the ones that build cameras and telescopes. For other physical sciences, you can have an experimentalist where you do your entire experiment within the lab. But in astronomy, we can't ever put a star in a lab and let it grow from birth to death. It doesn't work that way. So we don't really have those kinds of experimentalists. We do have people who are hybrid chemists and astronomers where they try to replicate the conditions in space in a chemistry lab, trying to understand the chemistry of interstellar dust or the chemistry of an extrasolar planet atmosphere. So you do get sort of hybrids with lots of other fields. You can have people who are geologists as well as astronomers, or chemists as well as astronomers, or biologists as well as astronomers if you're studying extraterrestrial life. So lots and lots of cross-pollination is possible and good. So as I said, I'm an observer. I get data from telescopes all over the world, but also off of the world, and I try to understand how stars form. It's important to remember that no astronomer spends all of their time at a telescope, except for the people who are actually paid to run the telescope. Most observers would be super lucky to get 5 nights per year. And of course, we never look through these telescopes with our own eyes. There's always a digital camera on the back of it. It takes a lot of time to turn data into papers, at least for me. Some people turn it around really fast, and I don't really know how they do that, but it takes a lot of time for me to reduce the data and be sure that every step I'm doing is correct and that I believe what the data are telling me. I work at Caltech, but I go to conferences and observatories all over the world. Astronomers travel a lot. What kind of astronomy do I do? Well, I study how stars like our sun form. We have a pretty good fairy tale that describes the big picture of how we think stars must form, but it has an awful lot of holes and assumptions that go into it. It is really not figured out at all. And a quote that sort of encapsulates that is, an astrophysicist is someone who sees something working in practice and wonders if it will work in principle. So what makes a star decide to form a disk? How does this process happen, and when? Does every star's disk turn into planets? How does that process happen and when? So lately, most recently, I've been studying time series data. So I have data which observes the same stars again and again and again, many times per day over many days. And I'm watching how those stars' brightnesses change with time. And that's a result of spots on the star's surface or texture in the disk that's around them. So there's lots of information embedded in this. And it's telling us something about what's going on very close to the star in these systems. How long have I been an astronomer? Well, I did my undergraduate thesis on galaxies using time series observations like the sort that I was just talking about. Here I am, 25 years later, still doing time series observations. When I was in college during the summers, I was working on the Compton Gamma Ray Observatory team, the OSSI team at the Naval Research Lab in Washington, D.C., which is where I'm from. I just want to emphasize that I had these undergraduate summer jobs working on gamma ray astronomy, and usually high energy photons means extragalactic. So in early graduate school, I was working with stellar abundances using ultraviolet spectra. In later grad school, I was using optical and near-infrared to study young stars, including time series data. My first postdoc, which is the first job after your PhD, I worked on mid-infrared studies of young stars, and my first quote-unquote real job was in the mid and far infrared for supporting the Spitzer Space Telescope, including studies of young stars and time series. You may have noticed a trend there. I'm sliding up in wavelength, down in energy. I've also used X-rays, but the only wavelengths I've not yet done at all myself are submillimeter and radio, but I have collaborators for that. So skills for a good astronomer. You have to have a lot of tenacity. You have to have a lot of attention to detail. I've seen lots of these, personality analysis things, and, we're supposed to tell you what kind of jobs to pursue. And I can put people I know, successful astronomers I know, in just about any bin in any of those personality tests. But I think we're all probably somewhere on the OCD spectrum, because we all have to have lots of attention to detail, and all of us also share a characteristic where we can just totally vanish into our work and emerge only occasionally to eat. where you just completely fall into what you're doing. And so I suspect we're all probably somewhere on the OCD spectrum. You have to have a willingness to work really hard, and you have to be self-motivated to do that. The external motivation just doesn't work for a good scientist. You also have to communicate really well in writing and in person, because it doesn't matter if you do good science. If you can't explain what you did, then that's a problem. In terms of classes to take, like I said before, computer programming, math, physics, astronomy, chemistry, geology, even biology. Now, one important thing that I want to call your attention to is this whole idea of fixed intelligence versus flexible intelligence. And there's a link at the bottom. So Chanda Prescott-Weinstein is currently a postdoc at MIT. She's a postdoctoral fellow in astrophysics. And she has a lot of good stuff that she writes. She's really into social justice and trying to get more people of color into the sciences. She writes a lot, and she's got a lot of stuff that even if you don't agree with it, it'll make you think. I really like reading what she has to say. But the reason I'm invoking her today is that she has a couple of columns on what it's like to be a person of color in physics departments and how to deal with things as an undergraduate or a graduate student. And a lot of her advice resonates, I think, with anybody who is a graduate student in the physical sciences. And so she has a special section calling out that fixed intelligence and flexible intelligence are two different things. You can choose, because intelligence is not innate. It can be taught, just like creativity is not innate. It can be taught. And so you have to learn to know the difference between really good preparation and intellect. And at the end of the day, what you believe about intelligence, whether it's fixed or flexible, has an effect on how well you do. And in the end, working hard really matters. So the fixed versus growth mindset, here's two examples. A fixed mindset would be to say, not everybody is good at math, so I shouldn't even try. Growth mindset is when you learn how to do a new kind of program or problem, it grows your brain. A fixed mindset would say, well, maybe math just isn't one of your strengths. A growth mindset would be to say, okay, well, if you catch yourself saying, I'm not a math person, you need to add yet to the end of the sentence. Learning is not always easy or comfortable, and you do have to work at it, but you are capable of learning anything you put your mind to. So I often get questions about job outlooks and salary. It's so hard to really answer this in a sensible fashion for the following reasons. NASA is less than 0.5% of the federal budget, and astrophysics is just a small fraction of that. The National Science Foundation, NSF, supports astronomy too, but at even lower levels. So if you go look up the Bureau of Labor Statistics, they lump astronomers and physicists together, and they get 23,000 astronomers or physicists in the U.S. I think that I don't know how realistic that is. I think there's probably about 8,000 professional astronomers in the U.S., but because of these numbers, small fluctuations in the federal budget makes an enormous difference in how many astronomers are employed. And moreover, actual salary numbers are kind of meaningless because, for example, the cost of housing in Kansas is going to be very, very different than that in Los Angeles. And there's a huge range of salaries between someone who's a research professor at a top-flight research university like Caltech or telescope operators who have usually only bachelor's degrees on mountaintops. So it's a huge range in salary. So a single number just doesn't encapsulate that. But I think when people ask for a salary, what they're really asking is, are you living hand to mouth? No. I make enough. I have a house. I have a car. I have a husband and kid. I have a normal life. And that's, I think, what people are usually asking when they ask for a salary estimate. So last slide I have here is hours. Scientists tend to work a lot. And when I was in high school, this sounded horrible. I could not imagine it because at that point, all I'd had were service jobs. And while they were fine, and fine for someone else to do more than 40 hours a week, I could not see myself doing those jobs for more than 40 hours a week. But what I didn't understand was that if you love what you do, it does not feel like work. And when I was in high school, I hated group projects with a fiery passion because I was the only person who cared. I was the only person on any of those groups who worked. But in the real world, everything is a group project. You cannot launch a spacecraft by yourself. So You have to work in teams. And it is so much fun to work with smart, motivated people, all of whom are pulling us in the same direction. It's fabulous. And it is, at the end of the day, completely ridiculous that I get paid to have this much fun. And my job is pretty flexible. I can leave early on Mondays and Thursdays to take my kid to Taekwondo, which I do. Or I can leave early to make a parent-teacher conference. The flip side, though, is that I'm reading email pretty much at all hours. So, it's a trade-off. But what I could tell my high school self was that working more than 40 hours a week doesn't feel so much like work if you really love what you do.